Let's get started. Hello, everyone. Good morning, good afternoon, and good evening to all our customers joining us across the globe. Welcome to the session 7 of the Arista TAC webinar series 2024. We were on a short break, and we are now back with a two-part session this year on debugging all things Arista and AI networking. Next slide, please. I would like to start by introducing myself. My name is Meetu Dubey, and I am a team lead here in the Arista Technical Services team. Today's session is presented by our technical experts from TAC, Sarthak Shetty and Vignesh Jyotinarayanan. A few quick pointers before we move ahead. We have the Q&A section of the webinar where you can ask questions, and our panelists who have joined in along with our speakers will help answer the same. You will also find the topology that has been mailed to you if you have registered with us before 23rd September. If not, you can find this in the chat. I have just pasted it right now. Next slide, please. For our customers joining after a long break or the very first time, this year we have delved into troubleshooting common network issues, including latency, drops, black holing, along with a three-part session on debugging multicast. These sessions and previous webinars from 2022 and 2023 can be found in the Community Central article linked over here. Additionally, we also offer customized training for our customers conducted by our TAC experts on features and platforms pertaining to their network. For more details on this, you can reach out to us on tac-custom-training@arista.com, or you can connect with your Arista account team as well. Now, before we step into the debugging scenarios, let us talk about what is special about the networks designed for handling AI network and how does it fit Arista Fabric in. When we talk about AI applications, we talk about consistent flows of large amount of traffic between the end nodes in the network. The nature of the traffic is such that it requires the network to have a high bandwidth and to support transport protocols that deliver the data or traffic at a very fast rate. Whether it is a small scale of applications or GPUs within a few racks, or a large scale of tens of thousands of end nodes, where the traffic may traverse a leaf spine architecture, or even a huge scale of up to 30,400 gigabit Ethernet nodes, Arista offers a variety of models that fit into these requirements. More of this is detailed on our white paper on our website, and we have linked that in the slide here as well. For today's session, our presenters will be walking us through the customer issues that were encountered pre-production during AI training job simulations conducted on an AI networking fabric built with Arista devices. We will see how these issues were identified and the fixes and recommendations provided to improve the performance of the overall network. With that, I will hand it over to the first speaker of the day, Sarthak Shetty. Sarthak, take it away.
Thank you, Meetu. Hello, everyone. My name is Sarthak Shetty, and I'm a Senior Technical Solutions Engineer with Arista TAC. Today, I will be discussing how to troubleshoot intermittent packet drops in an AI networking fabric. Before going into the problem description, let's talk a little bit about the kind of traffic and congestion management we will be using. Let's also take a look at the different acronyms. ECN stands for Explicit Congestion Notification. PFC is Priority Flow Control. RDMA is Remote Direct Memory Access. ROCE is RDMA over Converged Ethernet. CE is Congestion Experienced, and GPU stands for Graphics Processing Unit. So for all of these AI traffic flows, we are using ROCE v2 as a protocol. In ROCE version 2, the packets can travel across the subnets, whereas in version 1, the packets cannot travel across subnets. ROCE v2 flows are all mapped to traffic class 3 or TC3. Also, for the congestion management of these flows, we will be using ECN and PFC. So let's talk about ECN first. ECN stands for Explicit Congestion Notification. It is a feature that marks packets to indicate congestion. In the QoS bits of the IP header, we can see the ECN bits here. And here are all the values that the ECN bits can have. So you can see they can be marked as not ECT capable or ECT capable. ECT stands for ECN capable transport, which basically means it will support ECN mechanism. So you can see ECT1 and ECT0, both these values, they're considered to be functionally the same by the switch, and they mean that ECN mechanism is supported. If congestion is encountered, then the 0 bit will be flipped to indicate congestion, and that will give CE, congestion experienced, which is 1, 1 in binary. So that's the working of ECN. Here is an example with a diagram. So we can see there is a sender GPU sending Rocky V2 flows to the receiver GPU over here. The Rocky V2 flows are ECN capable, means they are marked as ECT1 or ECT0. The switch here now encounters congestion. Therefore, it will flip those bits and send a congestion experience mark packet towards the receiver GPU. Now, on receiving the CE packet, the receiver GPU will send a CNP or a congestion notification packet back to the source, back to the sender GPU. On receiving the CNP, the sender GPU will reduce its transmission rate. So this helps in congestion, in slowing down drops in congestion. ECN works between two ECN-enabled endpoints, and all devices in between must also support ECN. Let's take a look at the other congestion control mechanism, which is priority flow control. In PFC, if a device detects congestion, it sends pause frames to the upstream device only for that particular priority or traffic class. On receiving these PFC pause frames, the upstream peer will briefly pause the sending of that particular traffic class. Each priority or traffic class is configured as either drop or no drop. If a priority that is designated as no drop is congested, then that priority is paused. Here you can see there is a sender GPU. It is sending Rocky V2 flows to the receiver GPU with a switch in between. Now the receiver GPU encounters congestion. Therefore, it will send PFC pause frames for that particular traffic class. The switch on receiving the pause frames will briefly pause the sending of that particular traffic class. But the switch is also encountering congestion. So therefore, it will also send PFC pause frames to its upstream peer, which is the sender GPU. Again, on receiving these pause frames, the sender GPU will also briefly pause the sending of this traffic. Just like ECN, PFC also needs to be configured uniformly across all devices in the path. I also want to call back webinar 3 done in 2024, which speaks about flow control in detail. Now, priority flow control is an enhancement to regular flow control. The reason is we can send pause frames for a particular priority and traffic class with PFC. Whereas with flow control, with regular flow control, we would pause all the traffic on the link. Let's talk about one more tool, which is LANZ or Arista Latency Analyzer. This is a feature design which is used to detect microbursts that are undetectable using standard polling methods. It is a technology that tracks and logs buffer congestion and latency in real time, and it tells us about egress buffering. So here you can see we have interface queues or interface buffers. There is a high threshold and a low threshold. Whenever the buffer utilization goes above the high threshold, we will start recording congestion events. And this S here you can see is the start of the congestion event. This is the output of LANZ, which is by running the command show queue monitor length. So once it goes above the high threshold, we start recording events. We will keep updating the congestion events, which is the U here. We'll keep updating it until the utilization goes below the low threshold. And once the utilization goes below the low threshold, we will signify end of congestion. We'll say congestion has ended. All right, that was the prerequisite part. Now let's go into our problem description. Here is the network diagram. You can see we have GPUs here at the bottom on both left and right sides. They are each connected to their local leaf switches. So they are AI leaf 1, AI leaf 2. Then the leaves connect to the spine switches, AI spine 1 and AI spine 2. There's no VXLAN here. It's basic layer 3. Also, for the GPUs to reach each other, there's 4-way ECMP BGP routes from the leaves via the spines for the GPUs to talk to each other. Okay, let's take a look at the problem description. The customer just deployed an AI fabric and they ran some certification tests to confirm whether the fabric performance is as per expectations. In the test simulation, customers saw degradation in their performance. They also saw some packet losses, hence Arista was involved to help them figure out the issue. Now the goal here is to build a lossless fabric so that the GPU sync and the AI training job completion time will be as per the expected terms. Let's take a look at some key points to note. Whenever we are troubleshooting any environment, we always try to get some example flows to troubleshoot, as that will help us isolate the problem. So here also, many flows were impacted, but we picked these below 2 flows as examples to troubleshoot. So GPU 21 sending traffic to GPU 12. So here it is, GPU 21 on the right, sending traffic to GPU 12. Also GPU 22 sending traffic to GPU 12. We can see all the links in red here are all the possible paths that can be utilized for this flow, and this is because we have ECMP. Also, here is the process of troubleshooting which we'll be using so that we are clear on which step are we on. Now, let's go into the troubleshooting demo. Before that, I will recommend to please download the diagram which is sent so that you can keep it handy and it will be easier to understand the problem statements and the troubleshooting flow. I'm using a local copy for the troubleshooting demo, so let's start. Now, in the process, we have already traced the path of the affected flows. Next, we need to check which devices in the path are seeing packet drops. All right, let's take a look at our setup. We have SSH sessions to all our leaf and spine switches. So here you can see we have AI leaf 1 and AI leaf 2. And then on the right, we have AI spine 1 and AI spine 2. So now we need to find out which devices are seeing packet drops. For that, we can use the output show interfaces counter discards, and we can pipe it to NZ to only show us the non-zero values. So here we do not see any discards on spine 2, no input discards, no output discards. Let's check spine 1. Same output, show interfaces counters discards, pipe it to NZ. And we do not see any discards here as well. Okay, no discards on the spine switches. Let's go to the leaf switches. Right, let's check leaf 2 first. Same command, show interfaces counters discards, pipe it to NZ. Okay, no discards here as well. All right, let's check leaf 1, the only remaining switch. And here, okay, we do see discards here. We see input discards. This means the packets would not fit in the input buffers and hence they had to be dropped. Also, we can see the input discards are seen for Ethernet 7/1, which connects to AI spine 1, and Ethernet 9/1, which connects to AI spine 2. You can also see this depicted in the adjoining diagram. So now we have isolated leaf 1 as the only device seeing packet drops. The packets incoming from the spine switches are being dropped here. Here we could use CLI because we only had to check 4 switches. But if there are a lot of devices in your network, which will be the case for most customers, it will be very hard to check the CLI of each and every device. So in such scenarios, we can use Arista's Cloud Vision tool, which will show us everything happening on the switches on a single page. Here is how it will look like, the CloudVision's events page. As you can see, it tells us there's interface RX discards breached the threshold for Ethernet 9/1 and 7/1 of AI Leaf 1. So it's basically telling us there's input discards on these interfaces. There's also queue size event, but we'll talk about that later. For now, you can click on one of these interface discards events, and here you go. It will give you more details about the traffic rate, what kind of traffic is coming in, going out, what is the details and the status of this interface, and then most importantly, the discards and the errors. So it also tells us when did the discard start, when did it stop, and much more important information. So you can see the events page gave us all of this information in one single look itself. All right, now that we have isolated Leaf 1 as the only device seeing discards, let's check if any congestion is seen. We can use LANZ to tell us about microbursts and congestion. To check the output of LANZ, we can run show queue monitor length. Now, from the prerequisite, we remember that whenever queue length, the interface queue length goes above the high threshold, we will start recording congestion events. So these U, the type U you see here, that's the congestion events which we are updating until it goes below the low threshold. So we can see active congestion updates here happening every few seconds. The congestion is also happening for interface Ethernet 11/5, which goes to GPU 12, as you can see in the diagram, and traffic class 3. Rocky V2 traffic maps to traffic class 3. So we are indeed seeing congestion for the AI traffic, which we are concerned with. We can also see this output of LANZ in CloudVision if we configure the command queue monitor length streaming. Here is how it will look like in LANZ in CloudVision. So we can see the output of LANZ in CloudVision. You just need to find your switch, the interfaces, and then under the interfaces in the congestion tab, you can get the output of LANZ. All right, so this is how it looks like in CloudVision. Let's go back to our SSH session. Now that Leaf 1 has encountered congestion and Rocky V2 traffic is ECN capable, Leaf 1 should mark the packets as congestion experienced and send it to GPU 12. So let's check if Leaf 1 is indeed marking the ECN packets and sending it out. For that, we can use the command show QoS. And here we know that congestion is faced for Ethernet 11/5. So we'll just use that interface and then ECN counters queue. So we can see ECN marked packets, but they are for TXQ3. From the output of LANZ, it said TC3, traffic class 3, but here it's TXQ3. So we just need to do the mapping from TC to TXQ. And for that, we can use the output show QoS maps. So here it tells you the cost to TC mapping, the DSCP to TC mapping, vice versa mappings, but we are concerned with the traffic class to unicast transmit queue map. This AI traffic is unicast, so we don't need to be concerned with the multicast mapping. So here we can see traffic class 3 indeed maps to TXQ3. So the ECN marked packets are indeed for traffic class 3. Now, on receiving this congestion experience packets, the GPU 12 will send a congestion notification packet, a CNP, back to the source GPU. So it seems like ECN has been invoked properly. However, intermittent discards were still seen here. It's possible that the ECN threshold is not at a correct level to mark all the traffic. So we suggested to lower the threshold value so that ECN can mark all traffic and help with the intermittent drops. However, the customer did not want to change the thresholds because they had also deployed priority flow control, which is another congestion control mechanism. So they rightly wanted to know, why did PFC not kick in and why did it not seize the drops? So let's check the status of PFC and if any pause frames are seen. To check pause frames, we can use the command show priority flow control counters. And again, we pipe it to NZ to only show us the non-zero values. Now here, we do see RX pause frames incoming from 11/5. From the diagram, that means GPU 12 is sending us pause frames, which means it is telling, hey, I am not able to handle the amount of traffic you're sending me, so please briefly pause this priority. Similarly, we can see leaf 1 is also sending pause frames out of 7/1 and 9/1. So leaf 1 is also telling the spine switches, I'm not able to handle the traffic, please slow down, please pause this traffic. Now we know that PFC pause frame is sent for a particular traffic class. It is sent for a particular priority. How do we check that? How do we know which priority or traffic class were these pause frames sent for? You can also see the direction of pause frames in the diagram, right? So to check the priority of the pause frames, we can use the same command as before, but we'll just specify details with that. So show priority flow control detail. And here, as you can see, it tells us the priority. So we are receiving pause frames on 11/5 for priority 3, which is traffic class 3. And we are also sending pause frames out of 7/1 and 9/1 for priority 3, which is traffic class 3. So we are indeed receiving and sending pause frames for the AI traffic, which we are concerned with. The figure on the right also shows the entire direction of the incoming and the outgoing pause frames. We know that PFC config should be uniform across the path. So let's check the switches along the path, starting with the spines. But before that, let's just take a look at the troubleshooting flow to understand where do we stand. So we have already traced the affected flow paths. We have located leaf 1 as the switch experiencing drops. Now we need to find out why do we see these drops despite leaf 1 sending PFC frames towards the spines. We need to identify the reason for the drops. All right, so let's go to the spine switches and check the status of these PFC pause frames. Again, we'll use the same command to check the pause frames, show priority flow control counters, and pipe it to NZ to show the non-zero values. Okay, we do not see any pause frames here on AI spine 1. Interesting. Let's go to AI spine 2. Let's check if any pause frames are seen here. Show priority flow control counters. Okay, no pause frames seen here as well. So seems like the PFC pause frames sent by leaf 1 are not being seen. It is possible that these pause frames are not being honored by the spine switches. So in such cases, it's good to check the status of PFC. For that, we'll use show priority flow control. And let's run it on both the switches. Now here, Ethernet 1/1, which connects to leaf 1, this PFC status is D, which means PFC is disabled. Okay, and even 1/5, which also connects to leaf 1, the PFC status is disabled. But if you check further below 3/1, which connects to leaf 2, it is E and A, which means PFC is enabled and active, and also for priority 3, which is traffic class 3. Let's check 3/5 as well, because that also connects to leaf 2. Yes, it is enabled and active in priority 3 for 3/5 as well. So seems like PFC is disabled on the leaf 1 connecting interfaces. Let's check on spine 1 as well. Do we see the same things? Yes, indeed. 1/1 and 1/5 have PFC disabled. Let's check 3/1 and 3/5. Yeah, they have it enabled and active for priority 3. So it seems like on both spine switches, PFC is disabled on the interfaces connecting to leaf 1, whereas it's enabled on interfaces connecting to leaf 2. It is also depicted here on the image to make it more clear to understand. So when PFC is disabled, the incoming pause frames from leaf 1 will not be honored. Therefore, the spine switches will not pause the sending of the traffic class 3 traffic. The spine switches will also not send any pause frames towards its upstream peer, which is leaf 2, and hence there will be no back pressure created. Therefore, the source GPU will just continue sending traffic at the existing rate, and we won't see any seizing of the drops. So why this discrepancy? Let's check the running config of all of these interfaces involved to check why do we see PFC status disabled and enabled on them. All right, let's check 1/1. We see some speed config, layer 3 config. We also see ECN config. All right, that looks good. 1/5, same thing, speed, layer 3, ECN config, looks good. Now let's check 3/1. We do see the same speed and layer 3 and ECN config, but as you can see, there is an extra service profile AI scheduler applied here. Okay, let's check 3/5 as well. Yes, even this has the same layer 3 ECN config, but it also has this extra QoS profile AI scheduler applied, which is missing on 1/1 and 1/5. So let's check what does this profile do. Let's check the output, show QoS profile, and then the name, which is AI scheduler. Okay, let's see. Yes, this profile enables PFC and it configures priority 3 as no drop. The PFC priority command will determine if packets are dropped when PFC is enabled on the interface. So when we configure priority 3 as no drop, we are basically saying if congestion is experienced for traffic class 3, if any pause frames are seen, then it should be paused and not dropped. This will basically honor the PFC pause frames for traffic class 3, and if needed, it will also send PFC pause frames to its upstream peer. So now it makes sense that PFC is disabled on the interfaces connecting to leaf 1, and hence the pause frames were not honored, and therefore we continue to see drops. So this was for AI spine 1. Let's check if AI spine 2 has the same discrepancy or if something else is in play. So again, let's check the running config of all the interfaces involved, 1/1, 1/5, 3/1, and 3/5. Yeah, we see the same similar config, layer 3 ECN configs on 1/1, 1/5, 3/1. Yes, it also has the same QoS profile applied. 3/5, yes, it also has the same QoS profile applied. Let's check what this QoS profile consists of. Same things or something different? Seems like the same things. It enables PFC and then it configures priority 3 as no drop. So even with AI spine 2, the same things are happening. PFC is disabled, and for priority 3, it is not honoring the pause frames. So same discrepancy as spine 1. All right, let's check the troubleshooting flow now. We have identified the reason for the drops. The spine switches were not honoring the PFC pause frames, and this was because the interfaces facing leaf 1, they were not configured with PFC and the proper QoS profiles were not applied. So what's the next step? It's to fix these issues, fix the packet drop issues, and we just need to configure the missing QoS profile on the appropriate interfaces. So let's go to Ethernet 1/1 and 1/5, and let's apply this service profile AI scheduler. All right, it's applied here on spine 2. We need to do the same thing on spine 1 since it was missing here as well. So config mode, and let's go to interface Ethernet 1/1 and 1/5. And let's apply service profile AI scheduler. Okay, exit. And now that we have applied this, now let's check the status of PFC. So show priority flow control. Yes, there you go. 1/1 now has PFC enabled and active for priority 3. And 1/5 also has PFC enabled and active for priority 3, just like 3/1 and 3/5. Okay, now also let's check if the pause frames are being seen. Are they being honored? PFC is enabled, but the pause frame should also be seen and honored. So we'll use the counters command here and type it to NZ. Yes, we do see pause frames coming in from leaf 1. And spine 1 is also sending pause frames to its upstream peer, leaf 2. Therefore, it is creating back pressure. Right, let's check if spine 2 PFC status has changed. Yes, PFC is enabled and active for priority 3 for both 1/1 and 1/5. Let's check if the pause frames are being seen here now. So show priority flow control counters. Indeed, we do see pause frames coming in from leaf 1, and spine 1 is also sending pause frames to upstream peer, leaf 2. So both the spines are now creating back pressure towards the source. All right, so everything looks good with the pause frames. They are being honored now. So let's go to leaf 1 and check if this has helped. Okay, let's clear counters first because it's good to see the output from scratch. So let's clear counters. And now let's check if any more discards are seen. So same output as we used before, show interfaces, counters, discards. Let's pipe it to NZ. There you go, no more discards seen. We also like to use watch diff before any show command because watch will automatically refresh the output every 2 seconds and diff will highlight any differences. So this way you're not running the command multiple times to check if anything has changed. You can just see here with watch diff and we can see nothing is incrementing, nothing is changing. So there are no more input discards being observed on leaf 1, no more packet drops. So we have solved the problem. All right, let's just take a look at the troubleshooting flow before we end the demo. We have fixed the packet drop issues here now. The fix was to configure the missing QoS profile on the interfaces, and no further packet drops were seen after applying the profile. Okay, that brings me to the end of the troubleshooting demo. Let me just walk you through the troubleshooting summary, and I'll hand it over to Vignesh. So here was our network diagram. Customers saw packet drops in this AI network. So we focused on 2 flows to troubleshoot. The flows were GPU 22 and 21 sending traffic to GPU 12. The first thing which we noticed were input discards on leaf 1 on interfaces 7/1 and 9/1, which connect to the spine switches. We also saw congestion on 11/5, which connects to GPU 12. We saw that ECN and PFC were invoked. We saw PFC pause frames coming from GPU towards leaf 1, which were honored. And then leaf 1 also sent pause frames towards upstream spine switches. However, when we went on the spine switches, the pause frames were not honored. On further checking, we also saw that PFC was disabled on the interfaces connecting to leaf 1, whereas it was enabled on interfaces connecting to leaf 2. So we checked further and saw that the QoS profile AI scheduler was missing on the leaf 1 connecting interfaces. And this profile enabled PFC pause for traffic class 3. Therefore, the fix was to apply this QoS profile on this leaf 1 connecting interfaces, after which no further packet drops were seen on the leaf 1 and no further job completion problems were seen. So that brings me to the end of problem statement 1. I hope that was helpful. I will hand it over to my colleague Vignesh, who will continue with problem statement 2. Hey, Vignesh, all yours.
Thanks, Sarthak. Thanks for the great presentation. Let me go ahead and share my screen here. Okay. I hope you all can hear me and also see my screen clearly.
Yes, Vignesh.
Okay. Hello, everyone. I'm Vignesh Jyotinarayanan. I'm the speaker for the scenario 2 we have for today. That is another interesting scenario to look at where we are going to troubleshoot latency-related issues in the AI networking fabric, which was impacting the job completion time here. Let's look into the problem description now. So in this scenario, customer was able to see some degraded performance in their AI networking fabric when they were running high bandwidth AI training job simulation test by increasing the batch size to a higher value and also by tweaking few other parameters part of their simulation test. In this case, customer was not able to see any packet drops, part of a tracked statistics like switch drops and also RDMA stats and other things. So they were suspecting latency issue in the fabric for the slowness they were seeing on the jobs. Okay, and it was also impacting the job completion time of the AI training jobs. So they involved Arista team for troubleshooting this issue. In order to help us with more data points, out of multiple flows which were impacted during the same time, they were able to provide us with one example flow for troubleshooting, that is 10.2.5.2 while communicating with 10.2.2.2, that is GPU 21 communicating with GPU 12, was able to see the issues around the same time. And one more interesting thing is customer was able to consistently reproduce this issue whenever they were running this high bandwidth AI training job simulation test. And we all know that even though if one flow is impacted, it can still cause a straggler problem in the AI networking fabric where one or more processes running significantly slower than others will force other processes to wait for this slower one to communicate and synchronize between them. So this can hugely impact the job completion time and also bring down the overall performance of the fabric. Okay, so since we discussed about the problem description, let's also quickly discuss the topology we are dealing for today. You can see in the topology diagram, all the GPUs are connected to either ALEAF 1 or ALEAF 2. In order for GPUs connected to ALEAF 1 to reach the remote GPUs connected to ALEAF 2, it can use one of the four-way ECMP paths available via the AA spine 1 and spine 2. And all the ports in this topology are L3 ports, and it's a non-VXLAN design. And we are using BGP as a routing protocol between the leaf and the spines to share the routes. And all these switches you're seeing here are Arista 7060 series switches, which are designated AI fabric devices. And also to help prioritizing the Rocky V2 flows in this fabric, we are using QoS profile to prioritize the Rocky V2 flows in the traffic class 3 to help take it into a different queue so that we can handle it better. Okay, since we have discussed about the problem description, now it's time for us to discuss some of the key points to note from that problem description, which will be very useful for our troubleshooting now. So out of many flows which were impacted, customer was able to provide us with one flow, one example flow for troubleshooting, that is 10.2.5.2 while communicating with 10.2.2.2 was also seeing impact during the same time. So we can leverage this flow to trace the path of the flow in the topology diagram we have. And with that, we will be able to set the scope and focus on the devices and the links through which this flow were flowing through, right? And also they were not able to see any packet drops in the tracked statistics like RDMA stats and also the switch drops. So they were suspecting latency as the cause of the problem for the slowness. So we all know that latency issues are usually caused by congestion in the fabric. So that could be one or more points of congestion in the network, which we need to identify while troubleshooting. Okay. In order to troubleshoot these kind of issues, that is congestion-related issues, I have put together a process for troubleshooting which works fairly well. The first step is to trace the path of the flow in the topology diagram we have. This will help us understand the devices to focus on and the links to focus on while troubleshooting. And this is very helpful if you are especially dealing with a large fabric where you see hundreds of devices involved. Okay. After tracing the path, the next step will be out of the traced path and the devices which we are looking at, which devices or which links part of those devices are experiencing the congestion during that time. We need to figure that out. So once that's figured out, then we can move forward and trying to understand what could be the potential causes of seeing those congestion, right? So once that is understood, finally, we can deploy the fix based on the theory we have to fix the issue, and that will help us resolve the problem. Okay, let's dive deeper into each and every steps now. Okay, the first step, as we discussed, is tracing the path of the flow between 10.2.5.2 while communicating with 10.2.2.2. For that, I'm going to leverage the topology diagram we have here. So as you can see on the screen, GPU 12, it's connected to ALEAF 1. And GPU 12, in order to send the traffic to GPU 21, first it needs to send the packet to its gateway, that is ALEAF 1, via the directly connected link. And from ALEAF1, in order to send the packet to GPU21, it will take a look at the routing table, and it will be able to find the 4-way ECMP paths via AA spine 1 and spine 2. So it can send the packet either via AA spine 1 or AA spine 2. From the AA spine 1 or spine 2, it has a 2-way ECMP paths to reach the AA leaf 2 in order to send the packet to GPU21. And packet goes to A leaf 2, and from A leaf 2, it will be further routed downstream towards the GPU21 via the directly connected link. Okay. Even in the reverse path, the traffic is expected to take similar interfaces and the devices. So we need to focus on all the links which are highlighted in red on this screen, on this topology. And also, since the traffic can go via all the 4 devices time to time, so we need to focus on all the 4 devices while troubleshooting this. Okay. So with that, let's move forward with the next step in our troubleshooting, that is, out of the devices we traced in the path, which devices in the path were actually experiencing the congestion, and also which links part of those devices were also experiencing the congestion, right? So which will help us figure out the problem. So for that, there are a couple of ways. One way is to check the Cloud Vision dashboard for any events of congestion, because we already know that all the devices in the fabric is streaming their telemetry data to the Cloud Vision. That is one way to figure out which devices or which interfaces is experiencing the congestion. And the second way is we can directly log in into the UOS CLI to check for any congestion events on those devices, right? So since we are dealing with very less number of devices in this scenario, we are going to directly take a look at the UOS CLI. For that, I'm going to start logging into checking A leaf 1 and leaf 2 and spine 1 and spine 2. Okay. So before checking for the congestion points, I wanted to make sure that there is no congestion related discards happening on this fabric, because customer was mentioning that it was not happening. So let's validate that first before moving forward, so that our data points stay aligned. So let's check for that. The command I'm going to leverage here is show interfaces counters discards. So I'm going to execute that command on leaf 1. So show interfaces counter discards on leaf 1, and I was not able to see any discards incrementing on the A leaf 1. Okay, let's check what's the case on A leaf 2 as well. Show interfaces counters discards. I'm executing the same thing on leaf 2 as well. And even here, I'm not able to see any discards incrementing. Okay, let's also quickly check on spine 1 and spine 2 as well. Okay, on the spine 1, I'm executing the same command here again. And even on the spine 1, I'm not able to see any discards incrementing. Okay, finally, on A spine 2, I'm executing the same, and I'm not able to see any discards incrementing here as well. Okay, so that confirms and aligns with the observation that there is no discards happening in the fabric related to congestion. Okay, since we were suspecting latency related issues in the fabric, right? So we wanted to confirm whether we are seeing any congestion going on. So for that, I'm going to leverage latency analyzer outputs from the leaves and the spines to figure out whether there is any congested interfaces on this fabric. Okay, for that, I'm going to navigate back to A leaf 1. And on the A leaf 1, I'm going to execute show Q monitor length output to check for any congested interfaces. And I'm going to restrict the output to first 16 lines. And okay, we were able to see ET7/1 is one of the port which is congested here, and the congestion is happening for traffic class 3. And we all know that we are prioritizing the Rocky V2 flows in this fabric into traffic class 3. So definitely we are experiencing congestion for the Rocky V2 flows we are seeing in this fabric. And ET7/1, to note here, is one of the 4-way ECMP paths available to reach the spine. Okay. Let's quickly check what's the scenario for A leaf 2. On the A leaf 2, I'm executing the same command, show Q monitor length. And here I'm able to see the congestion happening for interface ET9/1 for its traffic class 3. And even this port is one of the 4-way ECMP paths available to reach the spine from the A leaf 2. Okay. Let's also quickly check what's the case with A spine 1 and spine 2 before we move forward with the next step of troubleshooting. Okay, on the A spine 1, I'm executing the same command, show Q monitor length. And I'm going to restrict for first 16 lines again. Okay. On the A spine 1, we were not able to see any active congestion going on, because if you notice the topmost line on the output, it is type E, which means the congestion has ended, and it has ended 39 minutes ago. So that means we're not experiencing any active congestion going on A spine 1. So we can ignore A spine 1 for now and move forward with checks on A spine 2. So I'm going to execute show queue monitor length on the A spine 2. Okay, on the A spine 2, we were able to see active congestion going on for the port ET1/1. As you see, the type flag as update, which means there is an ongoing congestion for the traffic class 3. And if you notice the diagram, and this is one of the ECMP paths available from A spine 2 to reach the A leaf 1. Okay. So the interesting thing here is we are seeing congestion on A leaf 1, A leaf 2, and A spine 2. And in order to figure out what could be the possible reasons we are seeing this congestion, we need more data points. The first data point I wanted to check is what is the interface utilization rate for these congested interfaces? Is it close to 100%? So let's quickly check that out. For that, I'm going to go back to A leaf 1 again and run with those checks. On the A leaf 1, I'm going to execute show interfaces counter rates output to check for the interface utilization around the same time. So with this output, I can clearly see that ET7/1 is the port which is congested as per LANZ output, and ET7/1 output rate, if you see closely, it is saying it's 100% utilized. And also one more data point to note here is, so there is a 4-way ECMP links to spine, that is ET7/1, 7/5, 9/1, and 9/5. Out of them, not all ports are like properly used. As you can see, there is some pattern of irregular load balancing observed here, where 7/1 and 9/1 are being used, and 7/5 and 9/5 are not at all being used when comparing their output rate. And even between 7/1 and 9/1, we are seeing irregular load balancing because 7/1 is used the most. Okay. So that is an interesting data point. Okay, let's move forward with the checks on A leaf 2. For that, I'm going to execute the same command on A leaf 2 as well. Show interfaces counter rates on A leaf 2. Okay, even on the A leaf 2, for the port which is congested, that is ET9/1 for its traffic class 3. And when looking at the counter rates, ET9/1 for its output rate, it is close to 75%. So it looks like time to time it is hitting this 100% mark and getting congested and showing that in the LANZ output. And but the one more interesting data point here is when we check the ECMP links to spine, out of the 4 available parts, we see one link is used much based on their output rate when compared to other links. That is ET9/1, 9/5, 11/1, and 11/5. If you compare that, their output rate, we are seeing this difference. Okay, even here we see a pattern of irregular load balancing. Okay, let's move forward with the checks on A spine 1 and A spine 2 as well. For that, I'm going to navigate back to A spine 1's CLI session. And on A spine 1, although we were not able to see any ongoing congestion, but let's quickly check for the counter rates to see what's the pattern here. Okay, in the A spine 1, we have 2 ECMP link set, that is 2 links going to leaf 1 and 2 links going to leaf 2. And here we see a pattern where the first ECMP link set that is going to leaf 1, out of them ET1/1 was used to 53%, while 1/5 was used only less. Okay, so even here we see a pattern of irregular load balancing. Okay, so let's quickly check in our last device, that is A spine 2, for the similar data point. Show interfaces counter rates. Okay, on the A spine 2, for the congested interface, that is ET1/1 for the traffic class 3 in the LANZ output, we see that is ET1/1. We see it's using 100% output bandwidth rate. And it's also part of the ECMP links to the leaf 1, that is 1/1 and 1/5. And even out of them, we see a pattern of irregular load balancing. Okay, so this leads us to a couple of questions here on why A leaf 1 and A leaf 2 was seeing congestion on its uplink. And even for those link, why we see an high link utilization despite we are having other ECMP paths, right? And also why the other ECMP paths we're actually showing less traffic when compared to others, right? So this is an interesting scenario, and in order to figure this out, first we need to actually quickly understand a couple of broad categories in terms of flows which we can expect to see on the switch. Okay, for that, let's quickly discuss about the mice flow and also the elephant flow. So mice flows are low bandwidth in nature. They are short-lived traffic, and also you'll expect to see many concurrent flows flowing through in the network. And with high entropy, it can be easily load balanced using traditional hash-based mechanism without us having to oversubscribe one particular port. Okay, and example of these flows are web browsing flows and DNS flows. On the contrast, elephant flows are high bandwidth in nature. They are long-lived traffic, and also you see very less number of flows when compared to mice flows in the network. And with low entropy, traditional hash-based load balancing methods won't be able to load balance it properly without oversubscribing one of those ports in the ECMP path, because the bandwidth is huge for these flows. Okay, and examples for these flows are storage backup flows and AI training flows. Okay, since we are dealing with AI training job and related flows here, so there is a possibility that we are hitting this elephant flow problem here. Because of this, we were not able to load balance it properly without oversubscribing one of those ports. So for this, in order to validate this, we can perform two checks. One is we can actually perform a packet capture on one of those highly utilized link for its outbound traffic, and we can perform a traffic analysis on the packet capture to tell whether we are seeing less number of flows, and also whether it is seeing any high bandwidth, which could match the pattern of elephant flow. Or we can leverage the S-flow sampling data available from the switch, which is already streamed to CloudVision, to tell based on the sampling rate to see whether we are seeing the elephant flows on the fabric, right? So since all the switches are already streaming those data to CloudVision, we're going to quickly log into CloudVision and check for those things. Okay, I'm going to log into the CloudVision here. Okay, on the screen, you're seeing the AA Leaf 1's dashboard for traffic flows. And the data source for this traffic flows here is the S-flow sampling, which is from the switches. And firstly, I wanted to take a quick glance over the flow records for the top 20 flows on how it looks like. And from this quick glance, we can clearly see that all the traffics here in the top 20 talkers are Rocky V2 flows based on their destination port number, that is 4791. And also looking at the DSCP value, it looks like it is mapped to the traffic class 3 as per our QoS profiles as well here. And okay, so let's take a look at the summary table to figure out whether we are seeing elephant flows here. Okay, so while looking at the summary table, for the span of last 30 minutes, we see very less number of flows flowing through this device. And even for these flows, if you closely notice the bytes and the packets, we see they are huge. So their bandwidth looks to be huge. So it clearly matches with the pattern of elephant flow, where very less number of flows are seen, bandwidth is huge, and also we see they are long-lived. Okay, so that clearly tells us that we are hitting this elephant flow problem here. Because of this, we were not able to load balance it properly using traditional hash-based mechanism without oversubscribing one port, and which was congesting one of those uplink and causing the issues in this fabric. Okay, let's quickly check for AA Leaf 2 as well, whether we're seeing a similar pattern. I'm going to check the AA Leaf 2 here real quick. Okay, on the AA Leaf 2 as well, while looking at the summary table, we were able to observe similar data points, that is very less number of flows, high bandwidth in nature, and long-lived flows. So matches the elephant flow pattern here. And let's also quickly check the AA spine 1 and spine 2, and we are expecting to see very similar flows, because the same flow is traversing through all the devices here. And even on AA spine 1, we were able to see very less number of flows and high bandwidth in nature. So elephant flows here as well. And finally, on AA spine 2, While checking it here, we even see less number of flows here. The reason is one of those leaves were hashing more flows to AS.1 when compared to AS.2. So, okay, so let's talk about the solutions here, right? So what is the solution we're going to pitch for this problem here, right? So we with the traditional hash-based load balancing mechanism, the elephant flows were not able to get load balanced across all the available links because of their high bandwidth, and it's oversubscribing one of those ports. We need to deploy some type of traffic spraying technique here for these flows to handle this better. Okay, in Arista 7060 devices, which we are using for this webinar scenario here, we can enable a feature called dynamic load balancing, where it works based on before allocating the egress port for a flow, it will also take a look at their data rate on that port to find the optimal port so that it can load balance the flows across multiple interfaces in an optimal way. Okay, so let's go ahead and configure this feature on the devices we have in this fabric here. For that, I'm going to go back to the CLI session and I'm going to configure the command IP hardware fib load balance distribution dynamic. Okay, so this command enables the dynamic load balancing feature on the ALEAF1. Likewise, I'm going to enable the same on ALEAF2. And let's also quickly do the same for AS.1 and AS.2 because we can see the similar problem even happen on AS.1 and SPINE2. Okay, so since we have deployed the configuration for the dynamic load balancing, now it's time for us to validate whether this worked. This worked and helped resolve the congestion issues. Okay, for that, let's ask the customer to restart the AI training job simulation test and take a look at the counter rates, right? So we are asking them and they are enabled it. And now let's go back to check the ALEAF1 and check the counter rates again. So show interfaces counter rates. Okay, while looking at the ECMP links now and their output rate, we were able to see better load sharing performance when compared to before. So all the 4 links are like fairly used when compared to others. So it's performing well now. Okay, likewise, let's also quickly check on ALEAF2. So show interfaces counter rates. Okay, even on the ALEAF2, we were able to see better load balancing performance after enabling the dynamic load balancing based on their output rate. Let's also quickly check whether the congestion things are resolved here. Okay, for that, we can use the show queue monitor length output on the ALEAF1. And while checking that, I'm not able to see any active congestion events going on ALEAF1. Okay, let's also quickly check the same on ALEAF2, show queue monitor length. And even here, we were not able to see any active congestion going on. Okay, similarly, we also need to perform the checks on AS.1 and SPINE2 to validate the fix worked or not. So let's go back and check the AS.1, show interfaces counter rates. And even here, we see better load balancing performance when compared to before when comparing the output rate. And let's check the SPINE2, show interfaces counter rates. Okay, even on the SPINE2, we were able to see better load balancing performance now. Okay, let's quickly check the queue monitor length to see whether the congestion is resolved, the congestion issues are resolved. The show queue monitor length, okay, on AS.1, and we are not able to see any congestion ongoing on AS.1. Okay, let's quickly check on AS.2. Show queue monitor length, output on AS.2. And even here, I'm not able to see the congestion happening. Okay, so this tells us that dynamic load balancing feature helped resolving this problem and helped with better load balancing for the Elephant Rocky V2 flows. Okay, so now let's go ahead and discuss on the troubleshooting summary we have here. So initially, customer was able to observe degraded performance in their AI networking fabric when they were running high bandwidth AI training job simulation test. And since they were not able to see packet drops in the tracked statistics, so they were suspecting latency issues in the fabric. So we were looking at one or more points of congestion in the fabric, and we picked one example flow for troubleshooting and tracing the path that is 10.2.5.2 while communicating with 10.2.2.2 during the same time was impacted. So we picked this flow for troubleshooting and deriving the scope. And after that, we were able to identify congestion issues on leaf 1 and leaf 2, and with the help of latency analyzer output and also interface interface rates from the USCLI. And this was due to high link utilization happening for those ports. And later we concluded that this was due to irregular load balancing happening for Elephant Rocky V2 flows in this A fabric. And we confirmed this with the help of S-flow sampling data from the Cloud Vision, which were streamed by the switches, right? And finally, we deployed the fix that is enabling dynamic load balancing feature to better load balance this elephant flows across the available ECMP paths. And that helped resolve the problem we were seeing in this fabric. Okay, so that's the wrap for the troubleshooting scenario we have for today. With this, I will hand over to Meetu for the closing note. Thanks, everyone.
Thank you so much, Vignesh and Sarthak, for a detailed and structured walkthrough on how to trace the impacted flows and identify where the congestion is happening. With that, we are at the end of our session. We have also shared a feedback form in the chat, so we would request everyone to please fill out the same. All the content, the recording, the slides, along with the Q&A will be made available on our Community Central page in some time. And we'll see you in our next session scheduled on 30th October. If you do have any questions, you can reach out to us at tacwebinar@arista.com. And we'll have the session open for another few seconds. Thank you so much and have a great rest of the week.